All right, we have some questions that we're dealing with for our take-home test. Let's just look at some concepts that we've been dealing with, and hopefully it'll help you do well in the test. Let's start off with moment of inertia. We have a rotating platform here. We know the moment inertia equation is equal to 1/2 mr squared. That's given to us by calculus. Okay, so we don't have to worry about the calculus. The formula will be provided. Now, what if another object, like a bucket here, would be placed on this rotating platform? And let's say the center of mass of this object is still a distance r from its center. So I'll draw a dot to represent that. So that is an r distance away. Now this object is completely rotating around this other object, so it is a point mass. So then I'm going to add mr squared to my equation. This piece represents the extra mass that's rotating around. And again, since it's a point mass, we go back to the original equation for it. So its whole self is going around somebody else. Okay, next question. What about trying to find the center of mass of an object that's a wire frame? Let's identify an origin, let's say the bottom left corner here. Then we have a center of mass right here of this object, a center of mass right there, and a center of mass here. Now let's say we have uniform mass density in all locations. And this is a length L, this is a length L, and this is 1/4 L. So the XY coordinate system of this one would then be equal to L divided by 2, comma 0. We're going to ignore the actual width of this. So we're going to call that right at 0. And the length of this divided by 2 would be the center of mass there. Now since this is length L, center of coordinate here is going to be 0, L divided by 2. Because again, we'll ignore the width of this beam here. And then up here, this is 1/4 L, so this is going to be 1/8 L right here. So this is going to be equal to L divided by 8, comma, and this will just be L. Okay, now what about the masses of each? Well, the linear density given to be the same for all, let's just make this beam here equal an m. This beam here would also equal an m. This would be m divided by 4, since it's 1/4 the length. So how am I going to get the center of masses for each of these? So let's go center of mass x here. Let's do this one. I'm going to then let that equal m divided by 4 multiplied then by L divided by 8. Okay, this coordinate here is 0, so I'm just going to plus an m times 0, and then plus an m here times L over 2. And I'm going to divide that by the total mass of the system, which would be m plus m divided by 4. Now what about the center of mass in the y direction? Well, we need to multiply their masses times their coordinates. So that's going to equal m over 4 multiplied by L plus L divided by 2 multiplied by m. Okay, then plus an m times a 0. Okay, and I think I'm missing a parenthesis here. Let's divide that all by m plus m divided by 4. So what we're doing, we're taking each of the masses multiplied by their coordinates and adding that all up, and then dividing by the total mass. And I guess I can add a parenthesis here also, because this is an m times a 0. Okay, and this is m times L divided by 2. And likewise over here, this is m times L divided by 2. And that's how you would find the center of mass of that system. Okay, next question. We have something rolling down an incline without slipping, and we'll give this an h value here. Okay, and we want to find the velocity at the end. So we have gravitational potential energy here, and when it rolls down, it's going to equal kinetic energy translational plus kinetic energy rotational. So when it gets to the bottom, it's going to be its center of mass located here, and will be moving, but this object will be rolling. That's why it's got two different types of energy. So then we'll go mgh equals kinetic energy translational is 1/2 mv squared, and kinetic energy rotational is going to be 1/2 I omega squared. Well, we can substitute things in for this. First of all, the moment of inertia, let's say this is a disk, is going to equal 1/2 mr squared. Okay, and remember W is equal to V divided by R. So again, W being omega, the angular velocity is V divided by R. So I'm going to substitute both of those in there. So I have mgh equals 1/2 mv squared plus 1/2 of 1/2 mr squared multiplied by V over R, that quantity squared. Okay, and then you can simplify that and cross things out. You can see that mass is in all locations that can cross off. You can cross off some R's over there too. And go ahead and simplify it when you're done. Okay, next question. What if I have a system with two different masses on it? Okay, and they're located at two different distances. Let's call this one R1. Let's call this one here R2. And when will this thing be in equilibrium? Well, it'll be in equilibrium when the torque going in this direction, this is positive torque, is equal to the torque going in this direction here. Okay, so what's torque equal to? Well, we know we've got force gravity going downwards here. And we, of course, have force gravity going down this way. So the torque will be force gravity multiplied by my rotation distance for both. So that's going to be then m r1, and then of course we got to multiply that by g, equals m r2, and multiply that by g. All right, now let's differentiate our m's to make it easier. Let's call this one m1 and this one m2, just so you can see it in my writing too. So that's m1 and this is m2. And then g's will cross off. So this will be in equilibrium when m1 r1 is equal to m2 r2. Okay, let's take a look at the next question here. We're looking at here, in this case, when something spins, what power is required, okay, to dissipate to stop it? So let's say we have something spinning, and I'll just do like an arrow here. This thing's spinning with an initial omega, just equal to W. And let's say in time t, this thing comes to a complete stop under some kind of a friction force. And I want to know what's the power it takes to dissipate this to make it come to a complete stop. So that's going to be energy loss due to friction, or there could be an outside torque acting on them. Well, we do know that power is equal to energy divided by time. So in this case, all of the rotational kinetic energy has to leave this object in a certain amount of time. So in this case, power is going to be kinetic energy rotational divided by time t. So what's that going to equal? Well, power is going to equal 1/2 I omega squared, because that's kinetic energy rotational, okay, divided by time. So that's our answer to that question there. Okay, hopefully those have helped. Movie 2 on this will be coming up very soon.